welcome you to the webinar today. And I will take a look at the debugging and tracing of the XMC7000 microcontrollers from Infineon with the Universal Debug Engine, the UDE, from our company. I give you a getting started into the debug tool UDE, and I will show you some of the basic debugging functions, especially for the XMC7000, which is a Cortex microcontroller. And then I will also give you a brief introduction how to use the debug tool for tracing the microcontroller application, for example, when you want to capture a program flow of your application. Before we begin with the debugging topic, I'd like to introduce very briefly the XMC7000 microcontroller. That is the latest device which is added to the industrial microcontroller portfolio of Infineon. The XMC7000 is based on the ARM Cortex architecture, and we have here a combination of a single core or a dual core Cortex M7 with a Cortex M0 Plus core. The Cortex M0 Plus is also called HSM hardware security module, and the Cortex M7 or both M7s are the primary application processing cores, and the HSM is handling all the peripheral and also security processing if necessary. For debugging and also for tracing the XMC7000, the ARM core side debug and trace interface or technology is implemented on the device. So basically, the XMC7000 follows completely the ARM standard or quasi-standard components, so core architecture, as well as also the debug technology that is used. As said before, the device is primarily aimed to the industrial market, but some of the peripherals are also interesting for some automotive applications. For example, electric two-wheelers. So on the bottom, you see all the target or the key applications. I've got this from the official Infineon documents here. Sorry for that. So the device, as mentioned before, has two different core architectures, a ARM Cortex 0 Plus and also one or two ARM Cortex M7s. And this has an impact on the software partitioning of that device. The device itself can be configured using the S-Flash into two boot configurations. One boot configuration is called the multi-core boot configuration, and the other one is the so-called single core boot configuration. It is a bit confusing because single core means you can also use the dual core ARM Cortex M7s, but it's kind of a monolithic software partitioning or software scheme here in that case. In the multi-core configuration, at first the Cortex M0 Plus, the HSM, is booting up. The main cores, the M7s, are inactive at that moment and are waked up by the Cortex, by the HSM. So that means you need two applications for or two binaries in this specific boot configuration, one for the Cortex M0 and one for the Cortex M7s. And in the single core configuration, you have only a user application for the Cortex M7s. In that specific case, the M7s are boot up directly, and there is no user application that is running on the HSM. So as a result, we have two different types of software partitionings. One is the heterogeneous one, where we have two binaries, one for the HSM and one for the main cores. And in the single core configuration, we have a monolithic application where we have only one binary that contains the code for the Cortex M7 main cores. For debugging, that means that we have also different requirements when you look at the debugging of multicore. So with the heterogeneous configuration with the HSM, it may be necessary to synchronize the cores for debugging in a partial way. That means maybe you want to only debug the main cores, then the main cores should be braked or halted at the breakpoint synchronously, but not the HSM. The HSM should be stay in a running state. This may be one of the requirements. Or you want to debug all the cores synchronously. That means all the cores are synchronized, or in a completely opposite case, we want to break the synchronization completely so that you focus only on one core, do breaking, single stepping only for that specific core, and the others are not affected and stay in running mode. We will see later how we how we can configure that. Okay, then let's jump to the debugger. Before we go to the debug tool, short look at the hardware that we can use from our tooling perspective for debugging a Infineon XMC7000 in our case here on such a evaluation board. That picture shows the simplest hardware setup for debugging. That includes the UED2 Pro from our Universal Access Device family, which is connected to the PC using USB, and then we are connecting using a standardized ARM or SWD adapter to the debug interface on the evaluation board. The only target-specific part in the debugger setup is this little adapter here. The access device box itself is device independent, so you can use it also for other projects, like with projects using an AURIX or other microcontrollers. The only thing you need if you change the target device or the target architecture is the appropriate license that you can connect and the adapter, as said before. Okay, then let's jump to the debug tool, and I'd like to start from scratch and show you how to set up a debugger session, and it's quite simple. You have two possibilities to control or to use the user interface of UDE. One is using the toolbar and another using the menu. I'd like to use the menu, and I create a new workspace, and the workspace is basically a file that contains all the settings for the debug tool and the target configuration for a specific debugger session. We type in a name. Okay, I had some preparations before, and I can leave this here. I use this name. You can type in whatever you want. And then once you press OK or open, you will be asked for providing a so-called target configuration, and the target configuration contains everything that is needed to connect a specific access device, a specific UAD to the device. There is a default button. This is always a good idea to use that. And if you press that, you get the complete list of all the supported microcontroller architectures. And then you can look for, in our case, Cortex M7. Vendor is Infineon. We have here the XMC7000 series. And if we unfold this, then we get the configuration for the particular board here. I press OK or finish, and then we save this target configuration as a file. I keep it here, and then we can select the target configuration from that list here. And once we have done this, the UDE asks us for which course we want to use the debug tool. We have the HSM in place. We have the Cortex M7s, the two ones, M70 and M71. And we leave it untouched here. You can decide it also later. If you want to debug only one core, then you can uncheck this, for example. But we keep this here untouched. Once we press OK, then we get a successful connection. You see this here on the message output. Here we have connected the HSM and also both M7 cores, and we see it also in the toolbar here. We have a status indicator for each core. So the HSM is in reset state, and both main cores are now inactive because they have to be activated by the HSM application. You see also that each of the cores are colored in a different way. So if you open some windows corresponding to a specific core, then you will see the colors again. That makes it very simple to keep an overview. The next step is, of course, loading the application that we want to debug. From the file menu, load program. And as said before, we have a HSM in place and also the two main cores. That's why we need two applications or two binaries. One for the Cortex M0. I select this. It's already compiled. We have an ELF file, we have an hex file. I select the ELF file containing both the binaries as well as the debug information. And then we get this window here opened. That window allows you to very flexible decide which application should be programmed in which core or in which flash memory. In this specific case, the HSM is the only core which is active at the moment. Everything has to be flashed using the HSM. We have a HSM application right now browsed in. We want to flash it using the blue binary checkbox. We want to load debug information into the debugger of the HSM. We have in this case no debug information for the other cores, so we untick these, and then we need to add the main application as well for the Cortex M7 cores. I browse in, for example, now the hex file, which only contains the binary information and no debug information. We flash the main application using the HSM. As said before, this is the only one which is active at the moment. If you want to debug this, it's always a good idea to use the debug information from the ELF file. So there's an option if you only browsed in the hex file, which we can check right now, and then the green checkboxes get available, and we can check them to load the debug information from the ELF file into the debuggers for the Cortex M7s. The ELF file is loaded automatically based on the name of the hex file. So if you have an ELF file with the same name, then this is done automatically by UDE. If you have a ELF file with a different name, then you will be asked to browse in the ELF file. Then we press OK. From the ELF file, we got the information that some source files should be opened for the main function and for the startup code, for example. If you get this window here, then that means that UDE can't find the source files on your PC at the location that is provided in the debug information. That may happen if you compiled the application on a different machine, or if you change the file locations in between. That's not a problem. You can browse in right now, but for now I skip this because I want to set up the debugger session in that way that UDE is able to find them automatically. I show this in a moment. Then we get the Flash tool opened, so we can now program the application to the Flash. And then I close this, and then we can start debugging. First of all, I'd like to see all my source files and tell the debugger how to find them. This can be done using the config menu and the debug server configuration here. And we have here on the left side some categories, and I browse, or I'm looking for the view server source code category. We have here two options basically on top. One is the aliases. Here is a list of all files that you have browsed manually. In this case, we have skipped these two files. I'd like to delete them because I want to tell now the debugger how to find the source files. And this can be done with the path management button. We have here two options. I use the first one. I'd like to define so-called replacement rules for the paths in the ELF file. I can add the rules using this button here, and then I get two input lines. The first one is the input line for the files that are present in the ELF file. I select this one. I keep it short and do it a little more generic, and then I need to browse for the location on my PC, for the actual location on my PC, which is somewhere here, and then I do this. Forgot. Okay. And then I do this also for the M7 the same way. Okay. And then we can start debugging. We can open, for example, the main function for the Cortex M0 for the HSM. I can run the application. I put this on. So, okay, so we have the symbols for all the three cores right now in place, and then we can start debugging. I open some watch variables. To do so, I select the core which I'm interested in using or clicking on by clicking on the toolbar buttons here, and you see this on the bottom here. We have now activated the HSM, or the HSM is in debug focus. Then I can open the watch window. I put it on the right side, browse for a variable. I can enable so-called periodic refresh. So we see something is happening on that core. And I do the same also for the Cortex M7s. I select or I activate the debugger fuse menu, watches, put it also on the right side, and then I browse for a some variables or a structure and enable the periodic refresh. And then we see, okay, we have some data. We have a clock here, which is counting seconds, minutes, and hours. And finally, I do the same also for the Cortex, for the second main core. Shared data, yes, that's the right one. And also enabling the periodic refresh. Okay, then we see, okay, what is happening on the while running. And then we can, for example, set a breakpoint. I can do this using the functions in the simple browser, for example. Yeah, let us set a breakpoint here in the updates clock. Okay, something is wrong with my simple information. Let me check. Yes, not bored. Okay, okay. And now the source file is opened automatically, and I enable the breakpoint window as well. And then I do it again. Update clock, and I set the breakpoint, and then we hit the breakpoint, and we can now do some single steps, or we look first at the status of the other cores. So if you hit this breakpoint, all the other cores are halted as well. This is the default. I mentioned before that we have implemented a debug synchronization of all the cores. And if I open, for example, also a window for the source window for the other cores, then we see, okay, we are halted also in the second main core here. And then I can, for example, do some single steps. And then we see that also the other main core do some single steppings as well. So we change the and you see also these yellow lines here. These yellow lines indicate the I say most yellow line is the active line we are on, and then if you do some single steps, then you see a shadowed yellow lines, which indicates the 5 previously executed source code lines when using a step. Okay. Yeah, then let's go. We hit the breakpoint again. And if you want to break this synchronization, then we have a tool that is called run control management, where we have defined a group of all cores that should be synchronized for debugging, and we can break that group. So for example, if you remove the core 0 from that group and you disable the breakpoint here, and then you make it go in that specific core, then you see only the core 0 is running. The others are still in halted state. You can manually select the HSM, for example, make it go. Then you see, because the core 1 and the HSM are still part of the run control group, that they are started together synchronously, and we can now set a breakpoint again. Then you see we stop only in core 0 while the others kept running, and then we can disable the breakpoint. And if you want to put it back, everything, then we have to stop all the cores. We can go back to the run control management and add the core back to the group, and then we can make it go again, hit the breakpoint, and you see everything is halted again in parallel. That is the synchronization feature. You can disable this completely if you want to debug the cores independently, but you have almost the complete freedom to decide which cores should be stopped at the breakpoint and which not. If you have an application in that case, or for such a dual core, it's not that important, but it's also a nice feature that we have in UDE, which can be used for shared code. Let me look at a function which is executed by both of the cores. If you set a breakpoint here in this shared function, let me show this also for the other core here. So if you look at this function here and we look into the machine code, then we see this is located at the same address. But if I set a breakpoint here for the core 0, and we do some steppings or some executions of that code, then we will never stop this in this function here if it's executed in core 1, because the breakpoint is always core specific. If you want to stop as in the second core as well, then you can, of course, add a breakpoint here. Then you stop also here in the core 1, but this could be very annoying, and for that we have a so-called multicore breakpoint, so you can change the behavior of that breakpoint and check this box here, multicore breakpoint, and then automatically we see the breakpoint looks a bit different, and it's set also on the other core. And if you look at the breakpoint window, then we see the breakpoint is basically or technically a single core breakpoint distributed to all the cores which have this executed shared function. And then if I make it go, then we see, okay, we stopped now in core 0, or now we are in core 1, and so on. Okay. Basically, these are some nice functions for starting debugging such a multi-core system like we have it with the XMC7000. Then I'd like to come to another topic, which is tracing. Tracing is useful, for example, if braking or single stepping would have a negative impact on the application's behavior when you in a debugger session. For example, if you have some parallel execution and you want to look at this parallel execution and some synchronization, then it's not always a good idea to break the system. Or if you want to investigate some timing issues in your application, then normal debugging using breakpoints is very often not possible or not sufficient. And then you can use trace, which basically observes the execution of the program without any influence on the runtime behavior. On the XMC7000, we have also trace available based on the core side from ARM. We have a ETM, which is the embedded trace macrocell, allows us a program trace of the cores. And we have also an instrumentation trace, which is somehow similar to printf debugging. However, you don't use a printf for that, which would have a lot of overhead. Instead, you can write using a command some application values to some dedicated stimulus ports, and these stimulus ports are then output as trace messages and can be then analyzed. You can use either a embedded trace buffer, an on-chip trace memory to store the captured trace information. And if the trace buffer is filled, then you can transfer them off-chip using the normal debug interface, or you can use a trace port interface where the trace information are transferred off-chip at runtime and stored in the debugger device, for example, in our UAD2 Next, where we have 512 megabyte trace memory available. This allows you longer trace recordings, and it is more or less the better method to do tracing with such ARM Cortex devices. For using the external trace option from our side, as mentioned before, the UAD2 Next is necessary, together with a trace module that can be plugged in, which handles the target communication and the trace port, the trace port here. And for using the parallel trace port, you need to set up the target a little bit different, because the trace pins are shared with the port pins of the device. So it's necessary to configure the port pins to be trace pins. This is prepared already in the target configuration that we provide in the debug tool, but not enabled by default, because sometimes you want to use the port pins for your application. That's why we have disabled these options. But if you want to trace using the parallel port, you have to enable this, and I'd like to show you how to do this in VUDE in a moment. This is the setup, the hardware setup that I actually use or have also used in the demonstrations right before. We have the UAD2 Next in place with the trace module plugged in. Here you see the standard debug adapter that we have already used in the demo before, but this is connected to the trace adapter, which allows you to transfer the trace data using the trace interface off-chip. Okay, and then have a look at the trace. So we want to trace for example, look at the the clock that we have implemented in our application. So I like to trace from the update seconds function. It's quite easy to set up the trace. I click right here, configure trace from function. And because I'd like to look at the wraparound of the minutes and the seconds here, I enable my breakpoint again, and then I can set up, change the variables. For example, this is like setting a test case, set the minutes to 59, also the seconds to 59, and the tenths of seconds to 9, which is the status or the state of my application right before the clock wrap around should occur or should be executed. The trace is right now ready to run. I'd like to change it a little bit for my use case here. Using the toolbar menu, I go to the config trace button here, and then I get this window. You see the trace is already configured for a program trace. We have enabled timing information, and we want to trigger the trace at the update seconds function. In the general tab, I can change my trace device. I use for the moment the ETB, but I set the trigger position a little bit further so that we see also some information right before the update seconds function is executed. Okay, and then we can open the trace window. And then we can start the trace. I disable the breakpoint and start the application. And application is right now started. The trace is automatically stopped because the trace buffer is completely filled. And I got a list of all the executed instructions, mainly the machine code. I can now go to the trigger, and I see here we trigger right before the update seconds function is called, and we see also the update minutes and update hours function, which are called also because we're now in the wraparound case here. I can visualize this also using the so-called execution sequence chart. It is a more a nicer view to the executed functions, and this takes a few seconds to be analyzed, and then I get all the functions here which are part of the trace recordings, and I can look at the what is happening here. You see we called the update clock function. This is calling the update seconds functions, update minutes, and update hours functions. That is quite nice if you want to look at the call hierarchy of your function or to measure some timings. For example, you have two markers here for measure timings, and you see the time difference. For testing, we have also, based on trace, some code coverage functionality. I'll put this also here, which allows you to look at the code coverage if you do automatic tests, for example. If you, for example, look at the update seconds functions, you see we have only a incomplete coverage here. The reason for that is that we never reach the increment of the seconds here in our trace recording. That's why we get a incomplete coverage of this block here and a 50% branch coverage for the decision that the seconds should be incremented. Okay, and finally, I'd like to show you how to set up the parallel trace interface at the very end. For that, we need to enable the HSM again and go to the target interface setup. The target interface setup allows you to specify some initialization commands. As said before, we have already prepared the initialization of the port pins for tracing in the target configuration, and here are the pre-configured settings, and you have to basically uncomment all the lines starting with the set command. And once we've done this, we have to disconnect and reconnect to the target to make these changes active. And now you can use the trace system again, but with the parallel port. I'll leave it that way, and then we can switch to the trace memory, trace window, started trace. I forgot possibly some of the settings to uncomment. Oh no, why it's not working? Okay, starting application, setting the parallel trace, okay, and then start the trace and start the application. Go to the trace window and we see that we captured also trace information here using the parallel trace port. And this allows you a much more longer trace recordings. We see this here in the topmost or in the header of the window. We have trace pages from 0 to 29, so 30 trace pages now are recorded. And if you look at the we have forgotten the ticks. Okay. Yeah, unfortunately, time is running out, so I'd skip now to show you the execution sequence chart. Right now, you would see a lot more trace information in it. So let's coming to an end for today. If you have any questions regarding that topic or other topics, then please use the webinar panel and drop us an email. We will answer these questions afterwards offline. I'd like to advertise also the next webinar, which will be in a little bit more than a month. And then I'd like to show you how to automate debugging and also automate testing with Python and UDE. And I hope you will attend and you will get the registration information quite soon. And yeah, finally, I'd like to thank you and have a good day.